Welcome back to All This Math. This is Professor Parker. Make sure you are subscribed to the All This Math YouTube channel. Like, share, do your thing. Do your thing. All right. So before we get started on this video about the real number system, where we're gonna classify these different numbers that I got up here, somebody hit me up on Facebook about this, so I wanted to look out and make a video because I'm not sure if I already have a video exactly like this on the channel already. So shout out to them who hit me up, which encouraged me to make this video. But this video was brought to us by some ancestors. Well, some of these brothers are ancestors, some are not. H. Rap Brown, right here, also known as Imam Jamil Alameen. He's a political prisoner. Shout out to him. Adam Clayton Powell Jr., Elijah Muhammad. Who else we got? Muhammad Ali, Tommy Smith, and John Carlos from the '68 Olympics. Huey P. Newton. Who else is on this joint? Kwame Ture, formerly known as Stokely Carmichael. I don't think you can see the rest of these people, so I'm gonna just say their names. Fred Hampton, Chairman Fred Hampton, out of the Chicago Black Panther Party. George Jackson, also a Black Panther Party member. Omowale Malcolm X, and last but not least, Robert F. Williams, author of Negroes with Guns and Radio Free Dixie, also a staunch advocate for the Republic of New Africa. If you've never heard of the Republic of New Africa, definitely look them up and do your research on them. There's a brother, Edward Onachi, I think his name is. I might be messing up his name. He wrote a book recently called Free the Land. Free the Land. So that's a book where you can get some information on the Republic of New Africa as well. All right, now into this. What we're doing here is we got 1, 2, 3, 4, 5 numbers, right? And one of the things we need to do in algebra is be able to classify numbers in terms of, excuse me, what type of numbers they are, right? In the real number system, because it helps us to better understand the numbers, right? Like, numbers have categories, right? Numbers can be classified into different groups. And it helps you when you get to higher level math also, because there are certain things that apply to certain numbers in certain groups that may not apply to other numbers in other groups. Also, when you do word problems, you may be asked about an integer. You may be asked about, a certain type of number, and you need to know what that certain type of number is. So dig this right here, right? These are the groups, right? You got your natural numbers, you got your whole numbers, you got your integers, you got your rational numbers, and you got your irrational numbers. Now, the natural numbers are just the numbers that you probably learned how to count with. 1, 2, 3, 4, 5, 6, 7, 8, 9, on and on and on and on, right? Nothing negative and not zero. Zero is not included, the negative is not included. Your whole numbers include all the natural numbers. You see how these groups overlap, right? The whole numbers include all the natural numbers plus the number zero. So the number zero and all the natural numbers. That's the whole numbers. The integers include all the whole numbers, so all the natural numbers plus zero plus all the negative opposites of all the natural numbers. All right, the negative opposites of all the natural numbers. So if 1, 2, 3, 4, 5 are natural numbers, -1, -2, -3, -4, -5 are the opposites of those. So those are integers. So all the natural numbers are the integers include all the natural numbers, all the whole numbers, and the negative opposites of the natural numbers. You can't have an opposite of zero because zero is just zero. It has no opposite, right? Now, the rational numbers are numbers like this, right? If you can represent that number as a fraction, right? And then when you divide, because a fraction is just a division problem, right? Now, rational numbers are probably the category that give people the most challenge. So I'm going to try to explain this, right? In as concise a way as possible. If you represent a number as a fraction, right? And then once you do the division, if one of two things happen. If you end up with a decimal that terminates, meaning it stops like 3.2, and ain't nothing after that 2, then that means that was a rational number, right? Or if you end up with a decimal that repeats and goes on and on forever, but notice I said it repeats, that means it's going at a pattern. That means it's also rational. So it could be two situations, right? Either it terminates, like 3.2 terminates at 2, and then nothing after the 2, right? It's just 3.2 that terminates. It could be 3.25. It could be 3.89, right? It terminates. That's rational, right? That makes sense. It's rational. Or it goes on forever, but then when it goes on forever, it goes on at a pattern. So it might be like 3.15, 15, 15, 15, 15, 15, forever and ever. Or it could be 5.891, 891, 891, 891. That's a pattern. It goes on forever and ever and ever, but at a pattern though. So it either terminates or it goes on forever in a pattern, right? But the first thing is to represent the number as a fraction. That's how I teach my students. Like represent the number as a fraction. That's why all natural numbers are rational. Why? Because if I take the number 5, right, that's a natural number, right? One of the numbers we count with, right? If I make a fraction out of that, and the way you make a whole number or a natural number into a fraction, all you do is write a fraction bar under it and put a 1. That's how you make any whole number, integer, natural number into a fraction. Just put a 1 for the denominator. Just put a 1 for the denominator. So 5 over 1 is 5 divided by 1. 5 divided by 1 brings me right back to 5. 5 is just 5. It terminates at 5. So it terminates at 5. So that makes it rational because it terminates at 5. You could even write 5.0 and say, well, it terminates at 0. Okay, fine. It terminates. It's not no whole bunch of numbers after the decimal point going on forever and ever. It ain't none of that, right? So that's what makes all the natural numbers and the whole numbers and the integers, even if they're negative, it makes them rational. Now, irrational, right? Notice the prefix ir in front of rational, right? So we know what happens when the number is rational, but what about when it's irrational, right? It's the opposite, the flip. So if you take a number represented as a fraction, do the division, and you get a decimal that goes on forever with no type of pattern, just something crazy, right? That means it's irrational, like a person that you can't understand, right? They just do irrational things. They're unpredictable, right? Irrational, right? Now, like 3.8712465938495251, like that's irrational. Just a bunch of random numbers after the decimal point. That's irrational. Another thing you should know is numbers like pi. You should memorize this. Pi is irrational because pi is 3.14159257 something and a millions and millions of numbers digits after that, right? So pi is irrational. Understand that. Anytime you taking a square root and the radicand, the number inside the square root symbol, is not a perfect square, that's going to be an irrational number. That's another thing for you to memorize. Just memorize that. All right. So like this right here, square root of 11. I know I'm jumping ahead, but square root of 11. 11 is not a perfect square. What are your perfect squares? Make sure you know what your perfect squares are. 4 is a perfect square because 2 times 2 is 4. Anytime you have a perfect square, whenever that number can be arrived at by multiplying a whole number times itself. That's why I'm going to say it again. A number is a perfect square if you can arrive at that number by multiplying a whole number times itself. So 4 is a perfect square because I could do 2, which is a whole number, times 2 to get 4. 16 is a perfect square because I could do 4 times 4 to get 16. 100 is a perfect square because I could do 10 times 10 to get a product of 100. 64 is perfect because of 8. 81 is perfect because of 9. 144 is perfect because of 12. 25 is perfect because of 5. 36 is perfect because of 6. 49 is perfect because of 7. Right? Those are perfect squares. So if you ever taken the square root of a number that is not a perfect square, that's irrational. And that's something for you to memorize. That's irrational. So square root of 11, irrational. Square root of 12, irrational. Square root of 13, 14, 15, irrational. Square root of 16, that's rational because that's going to equal 4 because 4 times 4 is 16. All right, square root of 17, irrational. Square root of 18, 19, 20, 21, 22, 23, 24, irrational, right? They're going to be irrational. Whenever you're taking the square root of a number that is not a perfect square, emphasis on the word not, capital N-O-T, not a perfect square. All right, I know I've been saying a lot. If you need to, run the video back, rewind it. You know what I'm saying? All right, now let's get into these. So, but also understand this. A lot of these numbers, they're in multiple categories at the same time. So, something else about, I didn't even get into, the integers. All right, the integers. Something else I left out about integers to help you remember. Integers can never be fractions or decimals. Integers can never be fractions or decimals. Integers can never be fractions or decimals. They have no fractional part, no decimal part. So 2.8 is not an integer. 1/2 is not an integer. Integers got to be basically whole numbers or natural numbers. All right, or the negatives of the whole numbers or natural numbers. So what are we working with here? So 3/4 is not a natural number. All right, so it's not natural. And what you want to do is you want to either have this list of groups written down or have them in your head, right? At first, you probably want to have them written down. So look at your textbook, look at a worksheet, look at your notes, right, from your notebook. Have these groups written down, and then just ask yourself, okay, is this number natural? No, it's not, because it's not one of the original counting numbers. It's not 1, 2, 3, 4, 5, 6, 7, 8, and so on. Right? Is it a whole number? No, it's not a whole number because it's a fraction. A fraction is a part of something, not a whole. All right. Is it an integer? No, because integers don't have a fractional part. All right. But is it rational? Let's see. It's in fraction form. What happens when I divide? Because a fraction is just a division problem, for real, for real. What's 3 divided by 4? If you put it in your calculator or you do long division or whatever division method you want to use on paper, you get 0.75. It stops at 5. It terminates at 5. It ain't no digits after the 5. All right. So it terminates at 5. So that means it's rational. All right. Now, if it's rational, that means it can't be irrational. It can't be rational and irrational at the same time. Right. Just like somebody can't be pregnant and not pregnant at the same time. Right. It's either one or the other. You're either going to be rational or you're going to be irrational. So if you're rational, you know you're not irrational. If the number is irrational, you know it's not rational. Right. All right. On to the next one. -8. Now, is that an original counting number? It's not, because it's negative, right? So the original counting numbers, the natural numbers, are like 1, 2, 3, 4, 5, and all that, right? That's not natural. Is it a whole number? No, because the whole numbers include all the natural numbers and the number 0. Is it an integer? Yes, it is. It is an integer because it's the opposite of one of the natural numbers, right? So it is an integer. All right. Now, what else? Is it rational? Yes, it is, because if I change this to a fraction and I do -8 divided by 1, because as a fraction, this would be -8 over 1. -8 divided by 1 equals -8, which terminates at 8. It terminates at 8. There's no digits after the 8. So that means this is rational. All right. So this is both an integer and it's rational. It's an integer and it's rational. And if it's rational, it can't be irrational. You can't be rational and irrational at the same time. All right. 2 pi. Now, I already told you about pi. Pi is a number that goes on forever and ever with no pattern. So pi is irrational. All right. So pi is not natural, right? Because we don't count with the number pi, right? It's not a whole number because the whole numbers include the natural numbers. It's not an integer, right? Because it's got a decimal component, 3.14 and all that. You know, Pi Day, March 14th, all that. Teachers bring in pizza and pies and all that type stuff, right? 3.14. And just because you multiply it by 2, that don't change the status. That don't change the status. It's just twice as irrational. That's all that means. It's just double the irrationality, right? Like somebody that's just already irrational, not even more irrational. All right, that's all that's happening right now. So 2 times pi just means that pi is even more irrational. So pi is irrational, right? Because it's not Now, why isn't it rational? Because this decimal that pi represents goes on forever with no pattern. No pattern, right? Just a bunch of random digits after the decimal point. And then we got 450. All right, let's go back. Run down the list. It is natural, right? Because we can count up to 450. That's natural. Even though it's a large number, it's still a natural number, right? It is a whole number because all the natural numbers are whole numbers. It is an integer because it don't have no decimal part to it or fraction part to it. It is rational. How do I know it's rational? It's rational because if I make this look like a fraction, it's 450 over 1. And then if I divide, it takes me right back to the 450. And if I got 450, 450 terminates at the 0. It terminates at the 0. All right. So we got, it's rational also. It's also rational. All right. So it's natural, whole, integer, and it's rational. This number is in 1, 2, 3, 4 different categories. All right. The -8 was in 2 categories. 3/4 was in 1 category. 2 pi is in 1 category. It's just irrational. Now, last but not least, and I already told you the answer to this one, whenever you are asked to take the square root of a number that is not a square, not a perfect square, it's irrational. It's irrational. If you put this in your calculator, it's going to give you a decimal. It's going to give you a long decimal with a bunch of digits with no pattern. No pattern, no rationality. So it's irrational. All right? And that's just something you can do. So you should be able to classify any number in the real number system that you're given. Now, when we start getting into like imaginary numbers, you get into like maybe late algebra 1, early algebra 2, dealing with the quadratic formula, solving quadratic equations and all that. We start getting into like imaginary numbers, which they're kind of cool. I like working with them. You know what I'm saying? But that's something different. So you got the real number system, and then you got the complex number system. The imaginary numbers are part of the complex number system, or rather, actually, I might have misspoke. I think the complex number system is the whole number system, and you got the real number part and the imaginary parts. You got real and imaginary, like how people be real and some people be fake. You know what I'm saying? It's kind of like that, right? But imaginary numbers are useful. Like we use them, right? That's like that's something else that's added on. It's not too difficult, but it's another category of numbers, imaginary numbers. All right. None of these are imaginary though. All right. So we got your rational, integer, rational, irrational. And just remember those rules I gave you, right? So pi is always irrational. The square root of a number that is not a perfect square, irrational. The square root of a perfect square is rational. Think about it. What's the square? 25 is a perfect square. What's the square root of 25? 5. 5 is rational because if you treat 5 like a decimal or treat 5 like a fraction, 5 over 1, you do the 5 divided by the 1, you get 5. It terminates at 5. So again, rationality, two cases, two conditions. The decimal terminates or it goes on forever in a pattern, like a beat, like a song that you like, right? 3.12, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. That's a pattern, right? That's rational. When it's a pattern, it's a rational number. All right. So I just want to make sure everybody know how to do that. Everybody know how to classify numbers in the real number system. And I got to get out of here. So go get some practice with this, and I'll see y'all in the next video.